Good afternoon, everyone. My name is Jianjun. I'm very glad that you have come to listen to my topic. First, please let me introduce us and my team. I'm Jianjun, a security researcher at the 360 Alpha team. I focus on Android system. And Guang, he is senior security researcher and team leader of 360 Alpha team, and he focuses on Android and Chrome. About my team, the main research fields of Alpha team are Android system security and Chrome browser security. We have found more than 150 vulnerabilities in Android system. In August 2017, we submit the first working remote exploit chain since the ASR program's expansion, and we won the highest reward in the history of the ASR. We have also hacked different targets in different Pong contests. These CVEs above are all discovered by us in the Bluetooth, and you can find them on the Android security bulletin. There are many security researchers hunting on Bluetooth, so duplicate is inevitable. Let's take a look at the architecture overview of Bluetooth for Android 7 and earlier. A Bluetooth system service communications with the Bluetooth stack through JNI and with applications through bundle IPC. The default Bluetooth stack is located in system BT. That one, block this BT. The stack implements all the protocols and the generated Bluetooth HAL, but Android 8 is a bit different. Let's have a look. The largest change in the native Bluetooth stack between Android 8 and the previous versions is the use of a tribal. Vendor implementations in Android 8 must use HIDL instead of live BT vendor. Vendor device interact with the Bluetooth stack using the hardware interface design language. HIDL divides the interface between the Bluetooth stack and the vendor implementation. If you want to learn the details, you can visit the Android official website. So you can see that two processes about Bluetooth. One implements Bluetooth stacks, and the other implements HAL. They use bundle to communicate to each other. The Bluetooth stack is much like the TCP/IP stack. Standard architecture structure. HCI is the lowest layer. It supports 3 transmission modes: basic rate, enhanced data rate, low energy. It is implemented in HIDL by manufacturers. The second layer is L2CIP. Logical link control and adaptation protocol. Like TCP, it supports various protocols, application protocols for different functions models like SDP, BNEP, LRCP, SMP. So L2CIP and above are implemented in the Bluetooth stack. I will introduce these protocols in detail later. Here example, I target with using Wireshark AVRCP packet. We can easily analyze the communication data and every field of AVRCP. The main code path is system BT. The latest version, Android 9, is a bit different from 8 and earlier, whose code seems to be more. Sorry. On Android 8 and earlier, it was compiled to be a dynamic link library named Bluetooth Droid.so, but lab Bluetooth.so on Android 9. The buggy code I'm going to talk about later is based on Android 8. Bluetooth stack is included in the past system BT stack. These subdirectors are very clear and implement different protocols. Bluetooth is an overall attack service, and each protocol is a sub-attack service. Next, I merely talk about 4 protocols: L2CAP, SDP, BNEP, and AVRCP, which have been discovered more vulnerabilities. So first, I will introduce L2CAP. The frame format of L2CAP is very simple. Its header is 4 bytes, 2 byte length field, 2 byte channel ID field. The payload is based on its CID. CID has 2 forms: fixed CID and dynamic allocated CID. Fixed CID can be divided into 4 types, although many types are divided in the code: single-link CID, BLE single-link CID, application layer CID, and others. Different channel ID represents different data channel processing methods. I will present later. When creating fixed CID socket, we have to set the value of struct member L2 CID, not L2 PSM. You can see that this one L2 CID, not L2 PSM. When you create fixed CID socket, dynamically allocated CID is allocated by using PSM. When you create a socket and specify the value of PSM, CID will be allocated dynamically. We can see that PSM seems like the port PSM seems like the port of TCP. Each upper layer protocol defines its own PSM value. For example, SDP's PSM is 1. When creating socket using PSM, we just set the value of the member of L2 PSM. The flowchart of L2 CIP attack value is attack vector is probably like this. When L2 CIP packet is received, it will be sent to the function L2C RCV ACL data. Based on the CID, the payload will be passed into different handler function. If the CID is 1, it will enter process L2CID CMD. Or it is 5, enter L2CBRE process seek CMD. Or if it is between 4 and 35, invoke the corresponding register function. Or not, invoke other handlers. Okay, that is the data processing flow. I discussed some bugs in these data processing functions. CVE 2018-9419 is an information disclosure vulnerability. It was found in the function L2CBRE process 6 CMD. Let's have a look. The argument P is it point to the packet sent by attacker. So see the line 6. CMD is assigned from the packet. We can make it equal to L2CAP CMD DIC REQ. Then lines 13 and 40 read 2 bytes from the packet respectively, but without checking the length of the packet. If all be read beyond the security end, we can see the line 17. If PCCB is null, the LCID and the receive RCID will be sent back to attacker in line 23. That is, information disclosure happened. The POC is very simple. We can just send 4 bytes data to the target device and receive the leaked data. The packet also simple. Check if all be read. The packet length is enough or not. Next one is the BNEP. The frame format of BNEP is not complicated. The first 7 bits represents frame type, and the S bit represents the extension. The BNEP source code is defined 5 types. From 0 to 4, BNEP payload is based on these types. As mentioned earlier, BNEP is based on L2CAP, dynamic allocated CID. It uses PSM value to register the BNEP handler to the L2CAP layer. The function is BNEP data IND. When L2CAP receives BNEP data, just call back this handler. BNEP data processing follow as shown above. When BNEP data is received, it will sent into BNEP data IND will be called back. After BNEP data IND plus the header, it will check tab. It will check the tab value. If tab is 1, call BNEP process control packet to handle control format. Otherwise, it will invoke PAN data buff IND CB and BTA PAN data buff IND CBAC to parse PAN data. CVE 2018-9356 was a double-free bug. It was introduced by the patch of another bug, 2017-1325 CB1857. Let's have a look at the patch in the function BNEP data end. Add one line, call OSI free. In function BTA pan data buff in INDC back, it has removed all the OSI free. Then let's analyze what's wrong with this patch and how it introduced new vulnerability. In function BNEP data IND, after handler BNEP header, it will call the function pointer p data buff CB, which point function pn data buff IND CB. After the end, call OSI free. Let's take a look at the function pn data buff IND CB. In function pn data buff in IND CB, there are several places that call OSI free. I choose the tracker 17, line 17. In order to do this, we need to meet the condition of line 8 and 9. SRC UUID is controllable, so it is easy to pass the check. DST is also controllable, but line 14 use DST to find the remote device connection. So DST must be the real attacker's device address. Therefore, we need a Bluetooth device whose address meets the limit of line 9. After line 17, it will return. After line 17, OSI free, it will return back BNE data IND, and OSI free, call OSI free again. That is double free. We can go on looking at line 22. Invoke function pointer pan data buff IND CB, which points BTA pan data buff IND C back. Let's have a look at this function. Yes, that is the function which removes all the OSI free caller in the patch mentioned before. Remove them here. Meaningless, isn't it? Actually, bdata pan data buff and the CBAC is not called by BNEP data directly, but instead called the PAN data buff and CB first. I don't know if the engineer who developed the patch or implied the patch thinks so. To track the bug, at least 2 BNEP packets need to be sent. Send a control. Let's have a look at the POC. Send a control frame. Send the control frame first, using correct PAN. Using the correct PAN UID to set up a connection first. Then send a BNE data format to trigger the double free bug. This is my personal views about patch. Before patch, have you mastered the code, the relevant code? After patch, whether the patch has been tested enough. Then I will talk about AVRCP. The frame format of AVRCP is is slightly more complicated. The header length is 9. The fields opcode, PDU, param length, and profile are important when handling bugs. We can analyze it with Wireshark. ARCP defines 5 opcodes, but when auding the code, the main constant is 3, 0x00, 0x7c, 0xff. Pixel supports 4 versions. The default is 1.4. ARCP supports 2 modes, controller and target. They communicate with each other on 2 devices. The source code of controller is in file AVRC parse ct.cc, and the target in AVRC parse tg.cc. AVRCP was introduced in Android 8, but it was refactored on Android 9. So here I just present Android 8. I only introduce the attack factor of the target. The controller is similar to this. Handle function handle RC mentor message CMD is the main entry to handle AVRCP data. Then pass the message to AVRC parse command. And it will check the opcode. 0x00 pass data to AVRC parse vendor CMD, or 0x7c sent to AVRC parse THRU, and then call or 0xFF invoke AVRC parse browsing CMD. Data processing flow is possible like this. CB18 13281 is a very interesting stack corruption vulnerability. I discovered the function AVRC parse browsing CMD. Let's have a look. Argument P message is pointing to the AVRC browsing profile data sent by attacker. Pbuff is pointing to an array on the stack whose length is 512. Line 4 reads the PDU from the packet when it is equal to link 0x80. Go to the line 17. Line 19 and line 19 read 2 bytes from the packet and assign it to strlen. So strlen is control error. Line 20, 21 and 22 and 23. If buffer is bigger than strlen, buffer is assigned to strlen. What's the encryptable code? If strlen is 1000, the buffer is also assigned to 1000, and then copy 1000 bytes into an array of 512 stack overflow. The check of 22 is meaningless. In addition, almost all case branches have experienced the vulnerabilities. The patch of this bug is very simple. Correct compression buffer len and str len. In controller and target handlers, there are a lot of switch case branches and, of course, a lot of critical bugs. The last protocol I will introduce is SDP. Its frame format is simple. 5 bytes header, and its payload is based on the PDU. SDP defines 7 PDU types, 3 for request and 3 for response, and 1 for error response code. Like BNEP, SDP is also based on L2CIP dynamic allocated CID. It uses PSM to register the SDP handler to the L2CIP layer. The function is SDP data IND. When L2CIP receives SDP data, just call back this handler. Attack vector of SDP is straightforward. For request data, call SDP handler client REQ and SDP DRSC server RSP for response data. In function SDP handler client REQ, call different handlers according to different PDU. The same as function SDP DIC server response. For example, if PDU is 4, process service ATTR REQ will be invoked. CB18 9478 is a memory corruption vulnerability caused by integer overflow. It was found in function process service ATTR REQ. To track the bug, we need to send at least 2 SDP packets. Let's take a look at the buggy code. Argument PREQ point to the data sent by attacker. Line 6 reading the data from PREQ to initialize ATTR SEQ. Line 9. In the first packet, we make this byte of PREQ equal to 0. Then go to line 13. ATTR offset is initialized to 0. Line 16 found an attribute from SDP DB database based on controllable variable ATTR SEQ. So we can think that P ATTR is indirectly controllable. From line 18, so we can see that REM len is also controllable. We make it a small value to meet the condition of line 25. Then SDP build partial ATTR RB entry will be called. Let's have a look at this function. First code, argument offset is 0, mentioned earlier. Line 11, let's have a look. Line 11, at ATTR len sub offset is less than len. So vulnerable len to core P is assigned to ATTR len with the first packet. Then go to line 16. Offset add len to core P and assign it to itself. That is, the OVZ is assigned to the ATTR len with the first packet. After the first packet was handed over, send the second packet. Let's go back to color. Line 9. In the second packet, we make this batch to 2, not 0. Then ATTR offset were not changed. Line 16, find a new attribute. Line 16, find a new attribute by the second packet. Line 18, REM len is controllable. We make it a big one in the second packet. Because ATTR offset is assigned to value, it's not 0. So it will go to line 26, 27. Core SDPU builds partial attributes entry again. So let's have a look at the function again. At the second time, argument offset is equal to the ATTR len found with the first packet. Line 6, ATTR len gives a new attribute length by second packet. So go to line 11, ATTR len sub offset and compare with len and get the minor one. What if ATTR len is less than offset? That is the buggy line, integer overflow. But that is unsigned int 16 minus unsigned int 16 and compared to unsigned int 16. What's the bug? So let's take a look at a small case. Compare the small case with GCC and C-line. Get the same result, -2. Let's the disassembly code. Compare with 32 bits registers and using JEP instruction. That is to say, compare a -b to len with signed integer. Sure, -2 is less than 16. So whenever 2 is equal the result that -2, convert by size t. Why is this? I can't find the conversions about GCC and C-line, but I found it in Microsoft WS. Because of the time, I don't talk about every clause, just to directly to the last code. Last one. If the operands are not double, are not floats, are not onside long, and not long, the compiler converts them into int type. Okay, let's go back to the barcode. ATTR len and offset are int 16, so they are all converted to int when sub. From the IDA, we can also see that compare with signed integer using LT instruction. Therefore, if ATTR assigned from the second packet is less than the first one, then to copy will be assigned a negative value, convert to when it was converted to size t, a very big value. So memory copy will be overflow. To complete the POC, you need to send 2 STP packets. In order to track the bug, the length of the attribute obtained from the first packet is greater than second. and it is necessary to precisely control other data so it can establish the correct state and pass the checks in the code. Vulnerable variable REC handler is the data offset, is data that affects the length of the attribute. In the first packet, REC handler is 0610008. So let's have a look at the second packet. In the second packet, REC handler was 0x10003 to make integer overflow. If you are interested in the POC, you can read the POC code from my GitHub. I will not explain in detail here. Earlier, I introduced some of the bugs I found. So how did I find these bugs? All bugs are discovered through code auditing. When auditing codes, combat protocol characteristics and vulnerability tabs. For memory compression bug, I focus on TLV format parsing code. Those are more prone to problems. For information disclosure bugs, just focus on these functions which send data back to attacker, and backtracing. Bluetooth stack is difficult to fuzz. Before handle fuzzing data, need to establish a connection, configure some params, and initialize a correct state. As long as any state is wrong, you need to restart the connection. In addition, a lot of protocols use state machine to ensure that data is parsed in the correct order. Any status error, the connection will be disconnected. That fuzz is a very efficient. How to find new attack service and vectors? We need to follow up on the stack code, looking for a new protocol or profiles based on the new channel ID or PSM. Refactored code. Actually, Android 9 has refactored some code. New field types, new processing function, and the end one to research Bluetooth SoC. In addition to these vulnerabilities, I also found some other security risks related to the design. First, attacker can make connections with the target device without any user interaction and authorization. As the code shows above, after creating a socket to target device and send data to the target device directly. Second, the attacker's state can reach the response process branch of upper stack, even if the target device does not send any request. For example, both AVDTP and GATT have this problem. The data processing path is judged only based on the field that the attacker can control. In response to these issues, I made some personal suggestions for improvement. Authentication should be applied when applying the upper layer connection. Check whether the device has sent the corresponding request before processing the response data. All of these problems include some other risky issues I have reported to Android security team. So, okay, let's make a conclusion. This talk, I introduced the Bluetooth architecture, Bluetooth stack and profiles, the sub-attack service and vectors, the service I hunted on Bluetooth protocols and profiles and the POCs. I also talk about how to find the bugs and new attack service and vectors and risky design issues and other improvements. Thanks to all colleagues at our team, I have uploaded this POC to my GitHub. If you are interested, you can get from it. Here is the reverberance used in this talk. So thank you for listening. Thank you.